All right, let's consider in this circuit the source-free RL circuit. And in this case, we're going to be interested in the current through the inductor, and we want to solve for the current in this case. All right, so let's go ahead and write this down. So since we are interested in the current through the inductor, we know that since the current cannot change instantaneously, we can determine its value as a function of time. Okay, so let's go ahead and write that down. Since current cannot change instantaneously, we can determine its value as a function of time. Okay. So again, we're going to start with an initial current passing through the conductor. Okay, that's we're going to assume there's some initial current going through the inductor. So we're going to say we'll take the initial current and we're going to say I at time 0 is going to equal to I big I naught. Okay, we're going to apply KVL around this loop for the circuit on the left, around loop, and what we get is V sub L plus V sub R has to equal 0, or we can rewrite it as L di dt plus Ri equals 0. Okay, so either of those work, where VL is equal to L di over dt, and VR is just IR. Okay, so we just plug those in, and we get this equation, and now we can further analyze this. So now we can do some integration, rearrange the equation and do some integration on this equation here. Okay, so if we rearrange this equation, let's say we have di over dt plus r over L times I equals 0. Okay, we can further rearrange the terms, and we can take the integral. So let's go ahead and let's rearrange the terms some more. Put di over dt on one side. Actually, no, let's just do di over I. Keep that current on one side. Okay, equals R over L dt. And then we take the integral of both of these here, integrate on both sides. So if we integrate this, what we get is, I'm going to simplify this some more. I'll take it step by step just so we can see what's going on here. So we have the integration here is going to be di over dt. It's going to be natural log of I is equal to minus r times t. So r times t over L. Okay, where this is going to go from 0 to I of t, and this is going to go from 0 to t. We can further simplify this as we take the exponential, we can actually substitute, then we'll take the exponential to get the final equation. So we take natural log of IT is minus natural log of I naught. This equals minus RT. That's not a sub t, that's R times t over L plus 0. Or if we rewrite this, natural log I of t over I naught equals minus RT over L. And now we do the exponential on both sides here. We do E here and E here. We can further simplify this. And then we get I of t is equal to I naught e to the minus RT over L. Okay, so this is the first step to finding the solution for the current. Just like we did with the RC, source-free RC circuits where we got the time constant, we can figure out the time constant for the RL circuit, and we see that the time constant for the RL circuit is going to be R over L, and so that's going to be tau is going to equal R over L. Okay. And then we substitute that back into this equation up here, and we can redefine I of t as I naught e to the minus t over tau, and that's how we find the current through that inductor. Okay. Of course, once we find the current through the inductor, then we can find the voltage across the resistor, and that's just going to be V R function of time is equal to IR, which equals I naught, just a matter of substituting, I naught R e to the minus t over tau. So this is the voltage, and then we can look at the power dissipated. Okay, in the resistor. Okay, and that's just going to be P equals V sub R I. Okay. All right, and then we can just substitute. The equation here. So we got equals. We said VR is I naught. VR is I naught R e to the minus t over t, and then so that's going to give us I naught squared R e to the minus 2t over tau, and that's going to give us our power dissipated across the resistor. And we can further, if we do some integration, we can determine the power absorbed by the resistor. We can determine the power absorbed by resistor. Okay. And we can, not the power, the energy absorbed by the resistor. Okay. So we can define this as W sub R of t is equal to the integral of 0 to t power lambda d lambda, and then we just further simplify this here. It's going to be I0 squared RE to the minus 2 lambda over tau d lambda, which equals minus tau over 2 I naught squared RE to the minus 2 lambda over tau, and that's going from 0 to t, where tau is equal to L over R in this case. Okay. And actually, I just noticed something. This guy back here, excuse me, this guy isn't R over L. This actually should be tau is equal to L over R. I had it mixed up. So this is the actual equation. So not this. Okay. All right. And then, or we can just rewrite it as WR of t in terms of time is 1/2 L I naught squared 1 minus e to the minus 2 t over tau. And that's how we get that energy absorbed. Okay, so now we've defined all the equations needed for the RL circuit. And again, we want to find, we just assume the initial current at time 0 is I naught, and we go from there to derive the equation as a function of time with the RL time constant tau, which is L over R, not R over L. And then we figure out the voltage across the resistor, the power dissipated across the resistor, as well as the energy absorbed by the resistor. And that's what we need to know about RL circuits to further solve equations.